Hello friends, in this video I am going to solve next exercise question from book Topics in Algebra. Question is, let G be the set of all real 2 cross 2 matrices AB 0D where AD, that is product of diagonal entries, not equal to 0. Prove that G forms a group under matrix multiplication. Further, we have to check whether G is an abelian group or not. We know that any non-empty set G with a given binary operation star becomes a group if star satisfies 4 conditions. Number 1, closureness. Number 2, associativity. Number 3, existence of identity. And number 4, existence of inverse. So, in order to check whether the given set G with a given binary operation is a group or not, we have to check all these 4 properties one by one. So, let's start our proof. The given set G is set of all 2 cross 2 upper triangular matrices with the diagonal entry product of diagonal entries not equal to 0. And the binary operation star is the usual matrix multiplication. First property is closureness. For this, consider any two matrices AB in set G. As AB are in G, we have product of diagonal entries A1 D1 not equal to 0 and A2 D2 not equal to 0. Further, we have product of matrix AB will be a matrix of this form. Now, observe that AB is again an upper triangular matrix. Now, product of the diagonal entries, that is A1 A2 and D1 D2, is equal to A1 D1 multiplied by A2 D2. Since both A1 D1 and A2 D2 are not equal to 0, we have product A1 A2 multiplied by D1 D2 is again not equal to 0. Thus, AB is again a matrix in set G, and this implies star satisfies closure property. Next is associativity property. We know that matrix multiplication is always associative. Thus, if A, B, C are any three matrices in set G, we have A star B star C is equal to product of matrix AB with C, which is equal to ABC, and again A star B star C is equal to product of matrix A with matrix BC, and that will be equal to ABC. Thus, star satisfies associativity property. Now, next one is existence of identity. Observe that 2 cross 2 identity matrix I will be a matrix in set G, as I is a upper triangular matrix and product of diagonal entries, that is 1 dot 1 is 1, which is not equal to 0. Therefore, 2 cross 2 identity matrix will be an identity element with respect to given binary operation. Thus, existence of identity property holds. Next property is existence of inverse. For any matrix A in set G, we have product of diagonal entries is not equal to 0. Now, for an upper triangular matrix A, determinant of A will be product of diagonal entries Since product of diagonal entries is not equal to 0, we have determinant of matrix A is not equal to 0. Further, we know that a matrix is invertible if and only if its determinant is not equal to 0. Thus, for given matrix A in set G, A inverse exists. Now, A inverse will be a matrix of this form, which is again an upper triangular matrix, and for which product of diagonal entries, which is equal to 1 upon AD, will be again not equal to 0. Thus, for given matrix A in set G, A inverse is again a matrix in set G. Therefore, for all matrices A in set G, their inverses are again in set G. Thus, existence of inverse property also holds. Now, from 1, 2, 3 and 4, the given set G of all 2 cross 2 upper triangular matrices with product of diagonal entries not equal to 0 is a group with respect to the binary operation star as a usual matrix multiplication. This proves that the given set G is a group. Now, further we have to check whether group G is abelian or not. So, let us do it. In order to check whether G is abelian or not, consider two matrices AB in group G. As A and B are in G, we have product of diagonal entries not equal to 0. Now, note that AB will be this matrix and BA will be this matrix. Here we can observe that these two entries are same. Now, note that for all real numbers A1, A2, B1, B2, D1, D2, A1, B2 plus B1, D2 need not be same as A2, B1 plus B2, D1. Therefore, for any two matrices AB in set G, it is not necessary that AB is same as BA, that is AB will be not equal to BA for all AB in group G. Therefore, G will be not an abelian group, and this proves our result.